in the break. So our next talk is going to be by John Lyons, who's going to go over geophysical monitoring. Take it away.
Yeah, geophysicists also work in pairs, but I don't want Ronnie standing right next to me because I don't feel bored. Yeah, so I just put this map up here. This probably goes without saying, but just to show the kind of or a reminder of the scope and a reminder that, one of AVO's primary missions is to detect and inform our stakeholders about activity at any one of these volcanoes really quickly, like 5 minutes or so. And to do that, we rely heavily on real-time geophysical data. And so I'm going to go through, most folks are probably familiar with the geophysical data, but I'm going to show what's available and talk about sort of what we do with the data and some potential research ideas for folks if you're interested or thinking about working on real-time data. Yeah, so we saw this yesterday. I'm going to talk about the seismic, infrasound, GNSS, and tilt data, all of which the short version of the talk is these are all publicly available and are transmitted in basically real time to EarthScope. So I'll start with sort of the very basic, which is seismic, and just looking at waveforms. We have, as Max mentioned yesterday, networks on 35 volcanoes. It's about 191 stations. These are now all, or I think almost all, 3-component, 120-second broadband seismometers. The data is all sent to EarthScope, and it's available if you want to grab it right now. You can look at this data in real time, with ObsPy or some other software, or with USGS software Swarm. We also generate network spectrograms every 10 minutes, and these are available if folks want to not generate their own spectrograms. You can just look at ours. We do some things in real time with waveform data, like the old tried and true, really not very sharp tool of RSAM, but we still use it. Here's one of our example of a spur RSAM alarm. So a potential research opportunity would be, developing some new waveform-based real-time or near real-time alarm. If you're so interested, AVO would be interested in working with you. Another primary usage of the data is, of course, generating locations for these earthquakes. Our earthworm system generates a bunch of STA, LTA triggers, and then if those triggers have a S-B time of less than about 5 seconds for the station closest to the vent, then which that equates to an earthquake within about 50 kilometers of the vent, then they're reviewed by a human analyst and located. And then they end up in the AVO hypocenter catalog, which is available. I think the AVO apps is internal only right now, but I think we're trying to make that public. But you can also get these at the USGS Comcat catalog. A really, I think, sort of a juicy potential research opportunity would be sort of a near real-time ML earthquake picker for the AVO catalog. This is something we've been talking about a lot. It's not going to be sustainable to pick all these earthquakes going forward. I think we've had a good run with our analysts, but we need to sort of leverage some new techniques, and we have an amazing training data set to throw at that problem. We also alarm from our hypocenter catalog. So here are 2 examples. We have an earthquake swarm alarm. So if some number that we set up ahead of time, if there are so many earthquakes within so much time, then we get this automated earthquake swarm alarm. We also have a large magnitude earthquake alarm. So if there's either an auto location or a reviewed location in the AVO catalog that has a magnitude above a set threshold, then we get an alarm. And these are just examples. We use a platform called Mattermost. It's sort of like Slack, and these are sent to that channel. This third empty space could be the alarm that you develop on the AVO catalog. Switching gears to infrasound, we have 9 6-element regional or more or less regional infrasound arrays across the arc to mostly to monitor for explosive eruptions and to monitor some of those volcanoes that don't have local seismic networks. These are all now broadband low noise sensors. They have wind filters and they're capable of detecting eruptions at hundreds or even thousands of kilometers. And again, all this data is sent to our scope in near real time. I should say the raw waveforms are not array process data. There are a bunch of research opportunities with this data. So, we're always looking for new and better ways to do the array processing that gives us information about signals sweeping across those arrays. You can look into regional infrasound propagation. The weather here is pretty wild, and it affects how infrasound propagates. And then there are things like automated mass movement identification, separating volcanic events from landslides, say. AVO does automate the array processing. So we process every 30 seconds of data with a 15-second overlap. So every 15 seconds, basically, we're doing the array processing. That goes to this web outpage, and you can see that array process data at that link. We're also outputting all the array data to a CSV file. So if you don't want to process array data, you could just use the stuff that we do. And you can see this gives us the waveform, how well correlated the event is, the trace velocity, and most importantly, the direction to where that sound was coming from. This is just an example of a Boguslav eruption back in 2017. We also, with the A to D expansion, we now have 10 networks that have 3 or more infrasound sensors co-located with seismometers. And we have a number of single infrasound sensors co-located with seismometers at other seismic networks. Most of these are within 15 kilometers or so of active vents. In the case of the networks, they can provide a source location, basically doing the earthquake problem, but in 2D. And single co-located seismometer or infrasound sensors are really useful for just confirming whether that seismic signal was actually just in the ground or indicated something was coming out of the volcano. And there's also ways to get basically a estimate of the source back azimuth using a co-located seismic and infrasound pair. In terms of automated processing, we do automated for the networks of infrasound sensors. We do this automated reverse time migration processing. So this is basically back projecting the infrasound in 10-minute windows. And we basically get a stack, and that stack indicates whether or not there's been a signal. So that those are 3 panels of noise, and then a signal from an explosion signal from Pavlov. This is built on the reverse time migration code that's up at the UAF GeoTools. This is an open source package if you're interested in running this. And then a potential research opportunity would be trying to do real-time, basically, inversions of detected explosions to get a sense of mass flux in near real time. So I've been talking about mostly things that we automate. So we're doing this automated processing. So we don't have to, if something is detected or an analyst is reviewing the data and they say, oh, there was some new activity, we don't have to go run a code manually. But we also do a lot of run a code manually. And this is just a smattering of sort of new techniques, more or less new. Some of them are pretty matured now, but this includes Darren's VoiceNet, WEX, envelope, sort of non-BT, tremor, or LP seismic location code, RedPi, some new seismic network coherence. Oops, sorry, the format got cut off. This is by David and a student of his, Logan Scamfer. This is a single station seismo-acoustic coherence, which gives you an estimate of the source back azimuth. So there's a lot of stuff that we do in near real time. That's not technically real time. But if you're interested in any of these please talk to us and be happy to work with you. Okay, so now I'm gonna switch gears. Do you want me to talk about this or do you want to talk about it?
Whatever you want to do it.
Yeah.
I can talk about it.
I had a good joke about one of those slides.
Well, send me the shout out your joke.
Alright.
I'll make space for you.
Okay.
Everybody's welcome. All right, so this was well reversed. Near real-time geodesy. So this is geodesy is kind of split up into two parts of talks. David is going to be covering the campaign GPS and INSAR aspect, which is less near real time than the GNSS, which is also not really quite real time. We have now on 13 volcanoes continuous GNSS, and on 3 volcanoes we have borehole tilt meters. The borehole tilt meters are grandfathered in from the PBO network. They've been out there. There's interesting signals. I'll talk about those. Here's a list of the volcanoes. You can see that there are, those are not massive networks. Those are monitoring networks for the most part. Thanks to AVERT, we have now 8. Let's see, where's the stick? The stick. I could use my arm. We have now 8 continuous sites at Orkmok, which is fantastic, right? Doubling the network. We have 3 sites at Cleveland, Akutan and Augustine and kind of Unimac volcanoes. They got a boost through the Plate Boundary Observatory. That's why there are so many stations there, which are really great. Notably, they are on. I think Akutan is close, but none of those are close to the NMU's recommendations for monitoring, which is a lot more of them. Let's see. So in summary, there's about 57, it depends on how you count, continuous sites that are operated by AVO, some inherited 12 borehole tilt meters. The data are downloaded daily. Right now, we're trying to move to a streaming model where the data are coming in real time and then backfilled, kind of like Earthscope's doing that. But right now, it's daily downloads of 15-second files. We have high rate sessions running, but because of telemetry constraints, those aren't necessarily downloaded unless there's important events. That sometimes includes large earthquakes. The metadata and the data, like all of that goes as soon as it arrives at AVO. I push it to Earthscope, so it's publicly archived. You have phase and range data available there in the metadata. We update the metadata after each field season to make sure that antenna changes and so forth are logged. All of that is publicly accessible. There's different ranges or lengths of the data records, obviously, depending on when the network was installed. Some of the earlier ones are early 2000s, Orkmok, or as recent as some of the latest installed sites are at Anchorage after the recent uplift that we recorded there. A lot of them then also use NODA sites as reference sites to get rid of tectonics and so forth. Okay, once we have the data, we run some QC on it. You don't have to read it, but we look at the quality of the data to make sure that it is usable or kind of get an idea of whether or not an antenna may be failing and inform fieldwork for the next season. And then we look at kind of returns for each network. What is the level of completeness of the data? This here is the Spur network, and thanks to the heavy lifting of the engineering group, that has pretty good completeness during the unrest, which is really nice. This here is a complete time series of station SPPG. So once we have the phase and range data, we run daily point positioning processing to produce these time series. And this starts in late 2004 and runs until now. You can see 2004 to 2006, there was inflation. Since then, this is North America, so there's tectonics still in there, but there was deflation, and now we have much more inflation at a higher rate. So that's pretty cool. If you want to know the details, we have a paper on that. all of the time series are available as these kind of static plots. There's integration into the public website that has happened, but there's also an API we can download them. There's an example a little later. We've experimented with real-time high-rate GNSS. It's possible. We have processing set up for that can be done, but really it's telemetry limited. It's kind of a question of how much for most of these volcanoes we really see, given the noisiness of real-time GNSS. But as telemetry gets better, we want to look at that. We then produce vectors. So this is red vertical, blue horizontal. Hopefully, trust me that spur is inflating indeed. This is from over the last year. Here is the scale. Those vectors, there are two levels of qualities. The API version basically looks at the time interval and does a linear fit to get at the trend and call that a velocity. And then we do more precise velocity estimation that also considers different error models for modeling purposes.
The geodesists have figured out how to use cats.
Yeah. Well, that's some of mine. I had a little thought for with that. Okay, that was a good one. Thank you. Tilt, we also do that. So this is a heavily underutilized data product. So if anybody wants to do research with a cat-like unwieldy time series that are tilt data, go for it. Also available through the API. At times we even have it bumped up to 1 second sampling during the Shishaldin eruption. What we're seeing here is kind of pre-event pressure buildup, and then there's a lava lake drainage event in the conduit. This is a rose plot. This is the station. This is kind of where Shishaldin summit is. It comes with temperature, which is also interesting because those data go back until the 2008 or so. This is a temperature record that shows seasonal. But there are interesting deviations that are going on in there. Those are 4 to 6 meter deep boreholes, right? So we haven't changed the sensors. There are the classic issues of tilt with drift and recalibration and so forth. But there might be cool stuff in those temperature time series. Okay. No, what did I do?
Took that very seriously.
Okay, so here's the near real time. This is the API. I put it on the slide so you have it in case the slides are available. But you can get the time series vectors and tilt time series. You can get it a station list with coordinates and so forth. That's all available. If you use some URL interpreter, there's a station name, there's a baseline. There's a format, maybe northeast up, or maybe you want radial transfers in up. Then you get a CSV file with some rudimentary comment information of what the columns are, and you have the data. So you could do that right now if you wanted to do anything with those time series. They are at times more quality controlled. Well, they're certainly more quality controlled and at times more complete than the UNR time series, right? So we actually do QC. We get rid of snow and ice on the antenna and so forth. So do you want to do the summary?
You should do it together.
Oh, let's do it as a choir. Okay, so the summary, we have a lot of near real-time geophysical data that is publicly available. Seismic infrasound, GNSS, and tilt. Use it. There's a lot of cool research topics that can be explored. If you want to know the ins and outs of the data, it is useful to collaborate or at least inquire with us, because there are, sometimes there are signals in there that we are very well aware of that don't have anything to do with the volcano, even though they kind of look like it. So it is useful to make use of the expertise of the people that have been looking at these data for a decade or more. There's real-time stuff available. Actually, the seismic data, I was recently on a research visit in Germany, and there was a guy who was doing real-time or machine learning relocations and just pulled everything out of Iris, and the next day had a new catalog. So there's cool stuff that can be done. Get in touch with us for questions. Thanks.
Any questions?
No. You can't avoid it. Single question.
All right, we'll find them during the break. We have one more